we name any point that it passes through. So we could choose either D or C here. I'm going to go with D. All right, so we started at A, we passed through point D, and then we keep going until we get to point B as the other endpoint, and we put an arc symbol over the top of that as well. So a major arc is always going to be named with 3 letters. And the last one we have right here is a semicircle, and that's a word that I'm hoping you guys know already. The prefix semi means exactly half, so a semicircle is going to be an arc whose measure is exactly 180 degrees, no more and no less. Now my purpose in drawing this diagram, or my hope, was that if we connected points A and C, we would pass right through the center of the circle with a diameter going right through that. And the important thing about a diameter is that it cuts a circle directly in half, and that's going to create 2 semicircles or 2 half circles in this figure. So again, with semicircles, we're going to use 3 letters. To name the top half, we're going to start at A, we're going to go through point B, and we're going to end when we get to point C. So arc ABC is an example of one semicircle. That's the one on the top. And if I felt like doing something different and naming the one on the bottom, we could do the same thing here, starting at A, this time passing through D and ending when we get to C. So we could call that bottom semicircle arc ADC. Okay, so the important thing to take from this, everybody, anytime we are naming a minor arc, we're going to use 2 letters. You can use 3 for a minor arc, but usually minor arcs are going to be named with 2. But if we're doing a major arc or a semicircle, we're always going to be using 3 letters every time that we do those. All right, let's take a look at this next definition right here, a central angle. Well, the name kind of tells you what it is. It's an angle whose vertex is going to be located at the center of a circle. So the center, everybody, is that point right in the middle where all radii meet, and every point on the circle is equidistant from that. So this angle right here, angle KLM, is going to be an example of a central angle because its vertex is right here at the center of our circle. Okay, and a nice thing dealing with this, and that's what these 2 figures down here are there to try to get you to look at and to see. If you have yourself a 90-degree central angle, think about what portion of the circle that seems to be cutting off. Kind of looks like a 90-degree central angle makes up about a quarter of that entire circle. Now, if the entire circle had a measure of 360 degrees, 1/4 of that 360 degrees would get you a 90-degree arc. If we think about a central angle here being a straight angle of 180 degrees, how much of the circle does that cut off? Well, that certainly looks like it's about half the circle, so that would be about a 180-degree arc there as well. And so maybe we're seeing a connection already. If a 90-degree central angle makes a 90-degree arc, and a 180-degree central angle makes a 180-degree arc, then maybe we'd be able to figure out what happens in each case coming next. So if we took a look right here at back to this page right here, there was a theorem written at the bottom down there, and this is the important concept right here, everybody. The measure of a minor arc is equal to the measure of the central angle that intercepts that arc. Okay, so in very general terminology here, everybody, if we had, let's see here, we'll get that guy out of the way. Okay, so if we had an arc right here that was simply labeled generically as x degrees for that central angle, then this arc up on top would have to be x degrees as well. Whatever the measure of the central angle is, the measure of the arc has to be equal to it. So let's knock out a couple of quick examples with this one here. Okay, we are allowed to assume from the diagram that this point right here is the center. That means that this 75-degree angle right there is a central angle, and here's the measure of the arc that it intercepts. So the theorem we just wrote down said that the measure of a central angle, 75 degrees, is equal to the measure of the arc that it intercepts, or cut off, 6x plus 3. And now it's a pretty easy equation to solve. We are just going to subtract a 3 from both sides. and that's going to get us 72 is equal to a 6x. Then we're going to divide both sides by 6 here, and we're going to get x is equal to 12. And we could double check that pretty quickly by putting the 12 back into this expression, but it's going to go pretty quick and easy. 6 times 12 is 72, plus 3 is a 75-degree arc here, which matches the measure of the central angle that it intercepted. And last example we're going to do today is going to deal with this concept right over here. All right, so we're solving for both x and y in this case. And so what we have right here is, again, a point that we can assume is the center of the circle. And so we know some things here. If this arc right here was 118 degrees, we know that this angle is going to be 118 as well. Or we could go the opposite direction. A 37-degree central angle is going to give us a 37-degree arc here. And I'm going to go ahead and cheat and use a concept that we're going to get to tomorrow. But if we can see that this point right here is the center of the circle, then we know that this chord cutting across must be a diameter. And that means if we have a diameter, that this arc right here must make up half of the circle and therefore must be 180 degrees. So that big green arc is made up of this 37-degree arc, this 118-degree arc, and this 4x minus 3-degree arc. So we're going to add those three things together and set them equal to 180. So we're going to write a 4x minus 3 plus a 37 plus a 118 all has to equal 180 degrees. All right, we've got some like terms we're going to combine there. So we've got a 4x, a negative 3 and 37 is 34. 34 and 118 is going to get us 152, and that equals 180. We're going to subtract that 152 from both sides and get 4x is equal to 28. We're going to divide both sides by 4. Will, what's 28 divided by 4?
7.
Look at that. So easy a 7th grader can do it. All right.
Yay.
So we get x equals 7 for that one. There was also a y in this problem, which I almost wrote over right down here. Well, the beautiful thing about diameters in semicircles is if you have one semicircle, that really means that you have two. So if the top half of this circle was 180 degrees, the bottom half is going to be 180 as well. So we're going to switch colors right here. We'll go to, let's stick with the orange right there. And we know that this bottom arc here of y squared plus 36 has to be 180 degrees as well. Now that square might worry you a little bit because we haven't seen much of that this year. It's what we call a quadratic equation, but this is a pretty simple one, so nothing to get too concerned about here. If we were to subtract 36 from both sides of that equation like we normally would do, that is going to get us, here we go, a y squared equals 144. And now, to get rid of a square, we're going to do the square root on both sides, and the square root of y squared is just going to be y, and the square root of 144 is going to be 12. All right, guys, that is a wrap for today. We'll pick the rest of this up tomorrow.